Hi, everybody, and welcome back. Today we're going to continue our discussion of organic molecular analysis with a focus on nuclear magnetic resonance spectroscopy. And in particular, today we'll be talking about proton NMR. If you haven't yet watched my video on carbon NMR, you'll want to watch that one first to get the basics of how NMR works and sort of the concepts. Today we're going to pick up sort of the second half of this PowerPoint lecture discussion focusing on proton NMR analysis. And so with that, I want to remind you of some of the language that we used before in regards to shielding. You'll recall, hopefully, that the concept of NMR requires essentially aligning all of the NMR active nuclei in sort of one direction along the axis of the instrument's magnetic field, and then using radio frequency to flip nuclei in the opposite direction and measuring their rebound. So we get a little bit of a signal for each nucleus, and that signal depends on its local environment, its local electronic and magnetic environment. So the language that we use here says that towards the low end of this display of the readout from the NMR, we would call this the upfield region or the high field region. And the nuclei that are going to show signals in this area are more shielded. They have more electron density around them in their local area. So typically on this end, when we talked about carbon NMR, we talked about alkane carbons showing up over here, sp3 and sp2 in sort of normal alkane carbons showing up in this area. As we start to get closer and closer to electronegative atoms, our oxygens, our nitrogens, halogens, things like that, or as we started to introduce aromatic rings or carbonyl groups, that sort of a thing, we were pulling electron density away from our nuclei, and so the signals that we see shifted more to the left, to the higher shift values over here. On the carbon NMR, these high values would have been in the neighborhood of 200 parts per million. On a proton NMR, we're going to be talking about something like 10 or 12 maybe at the high end. This is the downfield or low field region, and we would say that nuclei that create signals in this area are more de-shielded. They're closer to electronegative atoms. They have electron density pulled away from them, and so we end up with the signals moving from one side to the other. So we will see tables, just like we did for carbon NMR, that show us sort of generalities of where we can expect protons to display signals on this kind of a chart. What proton NMR does, if carbon NMR was good in allowing us to assess symmetry in particular, allowing us to assess the sort of overall structure of the molecule, maybe allowing us to distinguish between two different isomers, and looking at an ester linkage is a really good example. Carbon NMR is really valuable for helping us to determine sort of which direction the ester linkage is inserted in the molecule. What proton NMR allows us to do is to determine how many types of non-equivalent protons are present and what environment they're in. And so we're going to see what that means to be non-equivalent here in the next couple of slides. But this is an example of a simple proton NMR, and we can see the molecule that's being analyzed here. We have two different groupings of hydrogens in this case. We have the green grouping on the left, giving rise to a signal around 2 parts per million. And then we have our pink grouping on the right that's giving rise to a signal at a higher ppm value, a higher shift. Hopefully that makes sense at this point, that those pink hydrogens are on a carbon that's connected directly to an electronegative atom. And so we get this shift from the lower end closer up to a higher value. The green hydrogens are admittedly close to the ketone or the ester oxygen here, but they are connected directly, that carbon is connected directly to another carbon. So we sort of have one more intervening step before we get to that electronegativity. That's why we have a shifted, but not terribly shifted signal. Just for reference, if the oxygens weren't there at all, a typical alkane carbon hydrogen sort of a situation, those hydrogens would show a signal down here just below 1 part per million. So we can see that the green hydrogens are in fact shifted up a bit based on that ester linkage group being present, but they're not shifted as much as the pink ones that are connected directly to the oxygen. The reason that we see two signals from this molecule is that the pink and the green hydrogens are non-equivalent. So we have two groups of non-equivalent protons, each of which happens to contain 3 hydrogens. So how do we know if protons are equivalent? What we're really asking is, are they in the same electronic environment? Is their local environment the same? Now in this molecule, I hope it stands to reason without too much explanation that the pink and the green hydrogens are quite different. But if we look at a different kind of a molecule, and we look here at butane, for instance, you can see the convenient color coding for us. We would introduce a little bit of language here. So in this case, the green and the blue hydrogens would constitute two separate groups of non-equivalent hydrogens. These are what we would just call unrelated protons. They're just simply different. We can see by symmetry that the blue ones on the left carbon and the blue hydrogens on the right carbon are equivalent to one another. They're in exactly the same environment as one another, and so this blue group would represent all 6 of these hydrogens. They would give a single signal. And then likewise, the green hydrogens on the 2 internal carbons are equivalent to one another, again because the molecule is perfectly symmetrical. So this molecule would give us 2 signals on the NMR, one of which would integrate or would be representative of 6 hydrogens, and the other of which would be representative of 4 hydrogens. Now the test that's being shown on this slide is maybe not necessary for butane, but it's a good test to be familiar with. We can do this sort of replacement kind of a scenario. If we imagine replacing a hydrogen with something else, some other atom, X, whatever, and we look at what happens when we replace those, we can compare the 2 molecules that would result. So what's being shown here is if we replaced any one of the blue hydrogens with an X, we would get this top molecule. If we replaced any one of the green hydrogens with an X, we would get this bottom molecule. Now, whatever the X is, pretend it's a chlorine if you want to, we would get now constitutional isomers. If we get constitutional isomers from this test, we would say that those are non-equivalent hydrogens, and the technical word here would be that they're unrelated. In a practical sense, in NMR, that would tell us that the blue hydrogens and the green hydrogens would give us different signals on the readout. Now notice, it's not shown on the slide, but if we replaced one of the blue hydrogens on the right side, we would get this top molecule. If we replaced one of the blue hydrogens on the left side, we would get actually the same product. It would just be turned around in space. Now when that happens, we would say that those hydrogens are equivalent, and we would use the word homotopic. These 2 hydrogens give the same signal, or they're in the same environment. So in this case, all 6 of the blue hydrogens are homotopic. Imagine that the X here is chlorine, just as an example. If we replaced any one of these blue hydrogens with a chlorine, we would get 1 chlorobutane. It's just whether the chlorine was drawn here or here or here, any of these places around. If we replaced, likewise, any of the 4 internal hydrogens with chlorine, we would get 2 chlorobutane. Whether we numbered from the left or from the right, we'd get the same molecule. Since there's only one substitution product that's possible here, we would get the result that those hydrogens are equivalent. So again, all of the blue hydrogens are equivalent to each other. All of, on this diagram, the black hydrogens are equivalent to each other. What if we have a more complicated molecule? So we have here a molecule. This is, again, butane. Now we're talking about replacing these hydrogens in the middle carbons. And they're now showing us stereochemistry. Of course, that stereochemistry was always there. We just didn't show it on the previous diagram. Using language here called pro-R and pro-S. What this means is that if we were to replace this hydrogen, the blue one here, with an X, again, call it a chlorine if that makes you comfortable, we would end up generating the R isomer of this molecule. R2-chlorobutane. If we replaced the green one here on the top or on the bottom with chlorine, we would get the S isomer, so S2-chlorobutane. If doing this hypothetical substitution gives us a pair of enantiomers, we would say that those hydrogens are equivalent. We already knew that from the previous slide, but in this particular case, we would call these enantiotopic hydrogens. They're still equivalent. They would still contribute to the same NMR signal, but the word is a little bit different. So if we back up a second, technically these blue hydrogens we would say are unrelated. The green hydrogens, since we have the ability to generate a stereocenter by doing this substitution, we would say they're still equivalent. They're still in the same NMR signal, but we would call them enantiotopic if you were, choosing from a list of terms. Lastly, what if we already had a stereocenter somewhere in the molecule, and then we were generating a second one with our hypothetical test? Now, again, we do the substitution here. If we replace one of them, we will get the S isomer at that location. If we replace the other one, we would get the R isomer at that location. Since we still have one stereocenter that's unchanged, these two molecules would be diastereomers of each other. Technically then, that makes these hydrogens non-equivalent, and the word we would use to describe them, their relationship, is diastereotopic. Now, I want to throw out a little bit of a caveat here, and that's just to say that diastereomers, diastereotopic hydrogens, are often in very similar environments to one another. So depending on the strength of the instrument you're looking at, you may not be able to practically resolve the signals that these two hydrogens would generate. Technically, they're different. Technically, we would get two signals from this green and this blue hydrogen, but you may or may not be able to resolve them in real practical sort of application. So problems that you'll see using this language are problems like this. So if we look at a pair of hydrogens like these two, we would say, are they unrelated? Are they homotopic? Are they enantiotopic? Or are they diastereotopic? And again, some of them might be fairly straightforward to look at. Some of them might not be. But I encourage you to go through these problems and do those tests. Draw out the molecule with an X here, or separately with an X here, to see which one of those, what the relationship is between the molecules that you would get. And then you can decide which one of these four words applies. So in practical terms, if we were to take one of these, for instance, and so we'll take this one that's labeled as compound B, right? So if we just sort of forget that these are highlighted, this is just a cyclohexane with an OH group. This is cyclohexanol. If we look at the actual proton NMR for cyclohexanol, what we're going to see is this. So what are we looking at? Well, here's our standard scale. So we know that this is a proton NMR. We're going from 0 up to 10, 11, 12, that kind of a thing on our x-axis. Remember that the more alkane-like shielded protons are going to show up at low values. The more deshielded, close to electronegative atoms are going to show up further to the left. And so what we're seeing here are a couple of things. What I've labeled here in particular for us are the two sort of unique hydrogens in the molecule. Typically, the hydrogen attached directly to an OH group is going to be in the neighborhood of 2 to 2.5. Typically shows up as a very pointy, narrow, often pretty obvious signal. That's labeled as B here. The hydrogen attached to the same carbon as the OH group is affected by that electronegative pull by the electronegative oxygen. And so this hydrogen is more deshielded than any of the other hydrogens attached to the ring. We see it being moved up a little bit here, showing up just above 3.5, maybe 3.6 here on our scale, labeled as A. Now, the rest of this ring, there are two hydrogens shown in pink, obviously, but there are two hydrogens on each of these carbons. And so we have, by symmetry, one group of hydrogens Let me turn on a pen here for us so we can go up and label these. We have one group of hydrogens representing the hydrogens on these two carbons. By symmetry, these would be identical. So we have that one group there. We have the second group here. And we have a third group, another symbol here, right? So on paper, at first glance, we might expect 3 signals from this. Now, in practicality, as we just talked about, since we have a stereocenter on the alcohol carbon, or we will have had a stereocenter on the alcohol carbon if we did a substitution over here, we could end up with potentially 2 different signals from these guys, very slightly different. Imagine one of these hydrogens is above the ring in the same place as the oxygen. If we add some stereochemistry here, one of these hydrogens is above the ring with the oxygen, and the other one is a little further way below the ring. Same is true all the way around the ring. We do technically have a slightly different signal for these two, and a slightly different signal for all of these. But all of that ring hydrogen stuff is showing up in this, what I like to affectionately call a blob. Now, probably we have a signal sort of centered here, another one sort of centered here, and a third one sort of centered there, representing our circles and squares and triangles that I drew on that original diagram over there. But they're so similar to one another that they're all sort of overlapping and messy. When you see this kind of overlapping, messy stuff, that sort of indicates that you have different but similar signals amongst your protons that are causing those signals. So in this case, in all practical sense, we can see our alcohol hydrogen, we can see our alcohol adjacent hydrogen, and we can see the rest of the ring sort of overlapping between 1 and 2 parts per million. Taking another example here, we see an alkene. So this would be the structure shown here in the upper left, and we can see the assignments here of those peaks. So again, we see one hydrogen is significantly different to the others. That hydrogen is the vinylic hydrogen connected directly to the alkene carbon. And so that alkene, the magnetics of that alkene are de-shielding that one hydrogen because it's directly connected. And so we see it showing up way up around 5. So you'll see vinylic hydrogens in the table we're about to see show up in the neighborhood of 4.5 to 6.5, depending on what else is going on around them. Then we see 3 different signals for the hydrogens on these 3 methyl groups. Now, the hydrogens on each of the methyl groups are identical to one another. So we have 3 hydrogens contributing to one peak, 3 hydrogens contributing to a second peak, and 3 hydrogens contributing to a third peak. And by doing our substitution testing, we could sort of figure out that these 3 groups of hydrogens are slightly different to one another. We can see the numbers here. They do give slightly different peaks. And in fact, if we look carefully, we can sort of see those 3 groupings. But you can see how tightly clustered they are. So the higher the power of the instrument you're using, the better able we are to resolve things like this. If we did this spectrum on a very low power instrument, these might sort of mush together a little bit more. If we did it on a higher power instrument, we could zoom in on this scale. We could probably resolve these even better. And so that's the benefit maybe to having a really high quality instrument. I should say that these spectra that I'm showing you are real lab data. They're taken from the SDBS database, which is linked on the last page of the slide, or you can just search the internet for SDBS, the Spectral Database S something, and you'll find those out there. So in general terms, when you look at H-NMR, just like carbons, we see that idea of more shielded going to the right, less shielded going to the left. And so we see here our saturated hydrogens, our hydrogens on saturated carbons will be showing up at the near the bottom. We see those sort of getting closer to a double bond, the allylic hydrogens, a little bit higher up. We see then introduction of heteroatoms here, oxygens, nitrogens, halogens, going a little bit higher up yet. We see our vinylic, like we saw in the previous molecule here, a little higher. We see aromatic rings, hydrogens being up a little higher, 6.5 to 8, 8.5, something like that. The only things that you'll see higher than this, it's not shown on this slide, but it's shown on the next one, are the carbonyl hydrogens. So this table is really, really good. This is taken from the print version of our textbook. The online version, the data is all there, but the formatting is a little bit clunky for me. So if you want to print out this slide, that would be totally appropriate. But what we're seeing here are slight variations. Now remember that these are ranges and they're estimates. The local electronics of the molecule are going to tweak these a little bit. So for instance, if I had a tertiary alkyl hydrogen here, it says 1.4 to 1.8. Now, if the next carbon over had, for instance, was part of a ketone or was part of an ether linkage or part of an ester linkage, it's going to raise this up a little bit. I would expect that hydrogen now to be at the top end of this range or maybe even a little higher. So don't consider the edges of these ranges to be, cast in stone. These are just estimates to help you understand what you're looking for. So of particular use, a couple of things that I want to especially point out for us here. That hydrogen that's next to an alcohol or an ether. So the hydrogen next to that will show up in the 3 to 4 kind of range, 3.5 to 4.5. The alcohol hydrogen itself would show up again 2.5 to 5 kind of a range. Those are useful to determine if you have an alcohol present. So maybe you know that the molecule has an oxygen in it and you're not sure what context the oxygen is in. If you see this second peak, 3.5 to 4.5, that tells you probably have an oxygen nearby. If you see a sharp peak in the 2.5 to 5 region, that might point you in the direction of an OH group. We often have other information as well. So maybe you've seen an alcohol group in an IR spectrum for the molecule, for instance. That's one of those that we said was really quite an obvious peak. So having that or not having that can be very indicative of what's going on. Other ones that you'll want to pay special attention to are the aromatic ring. Almost nothing shows up in that 7 to 8 kind of a range. And based on how many signals you have there, you can sometimes pick out some information about what the substitution pattern is on the ring, if you have substituents on that ring. And then finally, of particular use are those peaks at very high shift levels. Anything above about 8.5, you're going to be looking at a carbonyl being involved. So an aldehyde hydrogen or a carboxylic acid hydrogen are going to be pretty much the only things that show up at those very, very high shifts. And so keeping that in mind can be helpful sometimes to determine what your molecule looks like. As an example, if we saw a molecule like this, so now we've got the structure shown to us, methyl 2,2-dimethyl propanoate. We haven't necessarily learned ester naming, but propanoate is going to indicate that we have a 3-carbon parent chain on one side of the ester containing that carbonyl group. And the methyl out front is going to indicate that we have a 1-carbon part of the ester over here. And then our 2,2-dimethyl would be our 2 branches like this. All right, so with that behind us, it has 2 peaks in its H-NMR spectrum. Well, what are their approximate chemical shifts? First, why do we have 2 peaks? Well, if we think about equivalence and our protons that we're talking about, we have one group of hydrogens. Here, all 9 of those hydrogens are equivalent to one another. If we replaced any one of these with a chlorine, we would get exactly the same molecule. And so we have one group of hydrogens here representing 9 altogether hydrogens that would give us a single signal on the NMR. And then of course we have this group of 3 over here that would give us a different signal. And so on our NMR we would expect 2 peaks roughly in a 3-to-1 intensity ratio, or 9-to-3, 3-to-1 simplified. So what are their approximate chemical shifts? Well, they're all methyl groups, and so if I go back and look at my table, I would expect them to show up at a very low level, right? But notice that this methyl methyl group that's connected directly to the oxygen, that should be pretty deshielded. And so maybe I would expect this one to show up above 3, something like the 3, 4, 5, somewhere like that. These guys over here, they're one step away from the oxygens, and so we wouldn't expect as much of a shift. They'd be higher than we would expect for standalone methyl groups, so maybe above a value of 1, maybe in the 1 to 2 kind of range, something like that as an estimate. If we go ahead and pull up the actual spectrum of this, we can see what's going on again with helpful color coding. So just as we predicted, we've got our 9 green hydrogens here, giving us a signal that's slightly deshielded based on where we would expect our normal alkanes to show up. And then we have our 3 hydrogen pink signal that's considerably more deshielded, showing up over here just above 3.5. What's shown in black right here is the integration trace. Now, a lot of the textbooks will still show it this way. This comes from way back in the day when we used to have these instruments attached to chart recorders, and paper would feed through at a consistent rate, and the readout from the instrument would be literally a pen that would drag back and forth and make the little marks on the paper. And so on that kind of instrument, you would have one pen that would generate your signal, so the actual NMR trace, and then you'd have another pen that could generate other information. And that's what this is. So when you see these integration traces, what we're looking at here is the height of this trace, this black line, is in proportion to the area under the curve from sort of calculus terms, and integration of the area underneath that green or that pink peak. And so imagine that this were drawn on sort of chart paper that had little graphic lines on it, grid lines on it. Back in the day, we would have counted the height of this thing by counting the boxes that it traversed. And then we would know what the relative area was. And so what we're seeing over here is a little integration table telling us that the peak at 1.2, so that's the green peak, has a relative area of 3 units, whereas the peak at the higher shift value has a relative area of 1 unit. So how are we going to use that? Well, if we know that there are 12 hydrogens in this molecule, then we can scale this up. So that 3-to-1 ratio becomes, I don't know why my pen is doing that, 9-to-3 if we scale it up to be 12 total hydrogens. This tells us that there are 9 hydrogens contributing to the green peak and 3 hydrogens contributing to the pink peak. In most cases, that would mean 3 equivalent methyl groups and 1 different methyl group. So the integration helps us to figure out how many protons contribute to each peak, so we can start to assign what the structure looks like. So far, this looks very much like carbon NMR. So far, we're talking about shielding and electronegativity and determining structure. Proton NMR gives us a little bit more information as well, and this comes in the form of those signals becoming split. So what we need to think about here is that the actual signal, the position of the signal, is dependent on its local magnetic environment, and that most of that magnetic environment is going to be set up by the instrument. Everything's being aligned in one direction by the super strong magnet of the instrument, but the local contributions of each one of these spinning nuclei contribute to what each particular nucleus feels. And so we can generate what's called a splitting tree to kind of show how this works. And I want to do that here before we kind of move on to the next slide, just to sort of give you an idea of what we're talking about. So imagine for a moment that the magnetic field of the instrument is here graphically. And then imagine that whatever proton is feeling this, maybe it has one neighboring proton on the carbon next to it. That proton next to it, its neighbor, would either be spinning in the same direction of the magnetic field or in the opposite direction of the magnetic field of the instrument. So it would either slightly increase or slightly decrease the overall magnetic field. So imagine, for instance, that our instrument's magnetic field is aligned in that direction. If the neighboring proton were also aligned in that direction, we'd be a little higher in total. Or if it were aligned opposite, we'd be a little lower in total, adding to or subtracting from the instrument's magnetic field. So what that means is that if the hydrogen that we're investigating, that should nominally have a signal right here in the middle, is next to one hydrogen, it could be in one of two states, that signal, instead of being in the middle, would actually be split into two peaks of equivalent size, a so-called doublet with a 1-to-1 ratio. When we see this kind of splitting, that tells us that the hydrogen we're interested in, the hydrogen we're interested in here is next to one hydrogen neighbor. Okay, and these are other things, whatever they are, not hydrogens. So the magnetic field of that neighboring hydrogen is influencing the environment felt by our first hydrogen. I'll show you more diagrams like this in just a moment, but what we're ending up with now is a situation where we can follow a mathematical tool that you may have heard about in a math class called Pascal's triangle to determine our splitting. So Pascal's triangle is going to help us figure out our splitting patterns. We're going to see that actually in just a few slides, so I'm not going to try to draw it here. But I'll show you an example. If we look at bromoethane, bromoethane has 5 total hydrogens as shown here. We have 2 groupings here. So we have the pink grouping of hydrogens on the carbon connected to bromine. We'd expect those to be fairly deshielded, being next to a halogen. And we do see that here, that peak showing up around 3.5. And then we see our blue hydrogens now another step away, less influenced by the bromine because they're further away. And we see them, again, still deshielded based on a normal alkane position, but not as far as the pink ones. We see our integration trace giving us, again, this relative area of 1 to 1.5. Or if we multiply that up, 2 to 3, representing our 2 and 3 hydrogens in these 2 positions. But our splitting rule for Pascal's triangle is going to tell us that we'll take our number of equivalent neighboring protons and we'll increase that number by 1 to get the split that we're expecting. So if we look just at the pink hydrogens for a second, our pink hydrogens have 3 neighbors. Those 3 neighbors, and I'll show you this on a diagram on the next slide, those 3 neighbors will split the pink signal into 4, 3 plus 1, into 4 peaks. We call that a quartet. And the ratios that we'll get are a 1 to 3 to 3 to 1 ratio. So if we zoom in on this pink blob, we see this 1 to 3 to 3 to 1. That tells us that whatever hydrogens gave rise to the pink signal, there was a group of 3 hydrogens on the neighboring carbon. Likewise, the blue hydrogen signal is in the position we'd expect it to be in, and if we zoom in on that, we see 3 peaks. That 3 peaks in a 1 to 2 to 1 ratio tells us that it had 2 neighboring hydrogens. And so these two together tell us pretty convincingly that whatever hydrogens caused the pink peak were next to the hydrogens that caused the blue peak. Or put another way, we had an ethyl group. We can see why this works on a splitting diagram on the next slide. So on the left of this slide, we see our methylene protons, the pink ones. And if we imagine that the instrument's field is pushing to the right, we have whatever the signal would be for those guys would be here in the middle. So that'd be our like 3.5 kind of number. We see at the bottom 3.42 would be our expected shift. But those 3 neighboring protons of the methyl group, the blue ones, either are all spinning in the same direction as the instrument's magnetic field, or they're all spinning in the opposite direction, or 2 of them are spinning with and 1 against, or 2 against and 1 with. And if you draw out all your possibilities here, there are actually 3 different ways that we could get this second peak, and 3 different ways we could get the third peak. That's where we get our 1 to 3 to 3 to 1 ratio. It's based on the probability here, the different arrangements that we could get. of those 3 magnetic spins. It's a little simpler on the other side because our blue protons only had 2 neighboring hydrogens. And so we have the case where they're both spinning in the same direction as the instrument's magnet, they're both spinning in the opposite direction, or 2 different ways we could orient one with and one against the magnetic field. So 1 to 2 to 1 ratio based on 1, 2, and 1. In both cases, these clusters or these signals are centered where we would expect them to be centered, but we see that characteristic triplet or quartet shape of multiple peaks. This slide also shows us the coupling constant. Now, coupling constant is a measure of how separated those peaks are. And what's kind of neat about this is that if we have 2 clusters, 2 different groups, the coupling constant is going to be the same if those peaks are being split by each other. So essentially, if the pink hydrogens are actually next to and causing the splitting of the blue hydrogens and vice versa, the coupling constant will be the same. If these pink hydrogens were somewhere else in the molecule and they were being split by some other hydrogens we don't have in this example, but being split by something other than the blue ones, this coupling constant would be different to this one. And so if we're given information about the coupling constant, we can try to assemble the molecule to figure out which ones are next to which other ones. If we look at a slightly more complicated molecule, so 2-bromopropane now, the structure shown to us on the slide here. Again, we have 2 fundamental signals from this. We have one signal given by the blue hydrogens. Those are all equivalent to each other. That signal would have a relative area of 6 based on 6 hydrogens. And we have this branch point carbon that has 1 hydrogen on it. That's different, right? We'd expect that signal, the pink one, to be more deshielded because it's closer to the bromine. And in fact, we do see that here. Our integration is 6 to 1, representing a 6 hydrogen and a 1 hydrogen signal. Now we look at the splitting. Let's look at the blue peak first. Those blue hydrogens have only 1 neighbor, that pink one. And so we would expect their signal to be split into a 1 plus 1, or a 2 peak, a dimer. And we see that here. So it's often called a doublet in NMR terminology. You see that they're the same height because there's an equal probability that that neighboring pink hydrogen is spinning with or spinning against the local magnetic field of the instrument. So we see this 1-to-1 ratio here, this doublet. That tells us that whatever hydrogens are causing this blue signal, it's being split by 1 neighboring hydrogen. Now the pink signal, if we look here, the pink hydrogen has 6 neighbors. So it should be split into 7 total peaks, that's 6 plus 1. And we see a little tiny one here, 1, 2, 3, 4, 5, 6, 7. And we see this sort of pointed overall signal, this pyramid kind of shape. That's going to be indicative of this splitting. So 6 neighbors gives us 7 peaks, a so-called septet. Pascal's triangle predicts what these should look like. So if we don't have any neighboring protons, we get just a signal, which obviously has an intensity of 1, some relative number. If we have 1 adjacent proton, like we just saw on the previous slide, we'd call that a doublet. We get 1 to 1. Now Pascal's triangle works by adding together the 2 numbers above where you're starting. So as we go down this triangle, this 1 would continue here. And then we get here 1 plus 1 to give us 2 in the middle. And then that one continues on the outside. That, if we have 2 neighboring hydrogens, we would call it a triplet. We'd have a 1 to 2 to 1 ratio. We saw one of those a moment ago. If we continue down, a quartet. So here's our 1 continuing. Now 1 plus 2 gives us 3. 2 plus 1 gives us 3. And then the 1 continuing on the outside. A quartet having 3 equivalent neighbors, we'd expect a ratio of 1 to 3 to 3 to 1. If we had 4 equivalent protons, which is possible with some symmetry and things like that, you'll see this occasionally, we'd call it a quintet for 5 peaks total, that's 4 plus 1, and they would have this characteristic ratio. And then we just saw the septet, that's 6 plus 1 is 7. That gives us our peak ratios like this. So there are a couple of rules to keep in mind. Chemically equivalent protons don't split each other. So for instance, if I have these three hydrogens in the molecule here in chloromethane, I would see only one peak. It's going to be one singlet because we're only being split by neighboring adjacent protons. Likewise here, if I look at this symmetrical molecule, these four hydrogens are equivalent to each other, so they would contribute to the same signal. There's no splitting going on. If one of these chlorines were something else, if that was a bromine, for instance, now the hydrogens on the right are different to the hydrogens on the left. They would split each other. I would get two different signals, each of which is split into a triplet, 2 plus 1. Splitting occurs only with neighbors, and it results in n plus 1 peaks. So what this slide is trying to show us is that these two, I wish these were different colors, these two protons would potentially split one another. They're close enough to have that local magnetic influence, but once we get 2 steps away, we typically don't see it. There are some kind of advanced cases where you sometimes might see long-range splitting, but for our purposes, we're going to say that doesn't happen. So only first neighbors. And furthermore, 2 groups of neighboring protons will split each other with the same coupling constant. I mentioned this when we talked about coupling constants before. So before we get into that, I want to look at this diagram, okay? We've got a complicated molecule now. We have 4 different types of protons. We have the methoxy protons over here on the left, directly connected to an oxygen. We'd expect those in that 3 to 5 kind of range right here. We've got our aromatic protons. I told you that those show up pretty uniquely in the 6.5 to 8.5 kind of range over here. Then we've got our carbon with no hydrogens on it. That sort of breaks things apart. And I have an ethyl group. And we've already seen what ethyl groups look like. I have the 2 hydrogen peak being split into a quartet right there. And I've got the 3 hydrogen peak being split into a triplet right there. Both of these are shifted up a bit based on having that ketone nearby, more so shifting for the blue ones than the black ones, just like we've seen before. What this slide is showing us is the coupling constant. If we look at the distance between peaks in the blue and in the black signals, those separations are about the same. That tells us that the blue proton signal is being split by the black protons, and the black signal is being split by the blue protons. Essentially, these groups are next to each other, and we can see that here. The aromatic ring protons, notice they're much, much closer together, but this signal and this signal have the same coupling constant. Now, why do we have 2 signals there? Well, it's a matter of symmetry, right? If we look at this ring shape, we have the protons on these 2 carbons are sort of close to the ether oxygen right there. They're equivalent to each other. They're kind of close to that ether oxygen. Whereas if we look at the other sort of shoulder positions, I'll switch to a different color here for us. If we switch to the other shoulder positions here and here, those are equivalent to each other. But they're further away from the ether oxygen, and they're closer to the ketone. And so we have the blue ones likely are these because they're one step away from an electronegative spot, and the red ones likely are the ones at the left. Either way, the red protons are being split by the blue ones, and the blue ones are being split by the red ones. Each of these positions has 1 hydrogen sticking off of it if we were to be explicit. And so the peaks are being split into doublets, so 1 neighbor. So we want to think about it that way. The hydrogen at this top left corner has 1 neighbor to split it. The hydrogen at the bottom left corner has 1 neighbor to split it. They're being split into 2s. Right. So the coupling constant lets us understand that the pink, even if we didn't know these were an aromatic ring, the signal here at 8 is being split by whatever's giving the signal at 7, and vice versa. the signal over here at 3 is being split by the signal at 1 and vice versa. So how do we put this together into a practical usage? Well, here's an example. Propose a structure for a compound with some formula that fits this data. And we're given information about shift. We're given information about integration, number of hydrogens, and we're given information about splitting. So first things first, we always calculate degrees of unsaturation. That way we know if we have a ring or a double bond somewhere we have to worry about. Remember that a fully saturated molecule would have the formula here of, I have to erase that, sorry, CnH2n plus 2. So if we were talking about being fully saturated for a 5-carbon molecule, we would expect 2n plus 2 is 12. Oxygens don't count in unsaturation. You can look up the unsaturation rules again if you need to back in the alkenes chapter. But we see C5H12, so we have no unsaturations. So no double bonds, no rings, no carbonyl groups, that kind of thing. And we see 12 hydrogens in the formula. If we look at our total here, we have 3 and 6, and 3 more is a total of 12. So everything is being shown to us. Most likely, our 3 hydrogens that are equivalent would probably be a CH3 group somewhere. Probably our 2 hydrogens are a CH2 group. We're not sure about the 1 hydrogen. 6 hydrogens is probably 2 CH3 groups that are equivalent to each other. And we see a singlet here. We see a triplet and a quartet, 3 and a 2, being split with the same coupling constant. That tells us that those probably an ethyl group. And so now we're starting to build a molecule. It seems like I likely have an ethyl group based on those 2 parts of things. I've got a singlet, 1 hydrogen that's not particularly shifted. So it has no neighboring hydrogens. And I've got a 6 hydrogen group that's being split again into a singlet. So 2 methyl groups connected to something with no hydrogens on it. I want to look at how I'm going to break this thing out. And so you can start to build up molecules like this. And this is what this would actually look like. I want to back up just 1 second and point out, notice how close together these 4 groups are. 0.92, 1.2, 1.5, 1.6. We see this absolutely tragic overlapping mess of junk here. If we were to zoom in quite a bit, we can see our signals. And this particular one was not taken on a great instrument, but we can see, those individual signals showing up for us. One thing that you may end up seeing with complicated molecules is what is often called complex splitting. This is where we have non-equivalent protons that are splitting one another. So I'm going to show you a couple examples of that. One of which is toluene. Toluene is methylbenzene. And so it looks like this. We have 2 sorts of types of protons, if you will. We have the methyl protons that are equivalent to one another. So we see that signal over here around 2 1/4. And then we have the aromatic ring protons. Now, sometimes it's easy enough to just say, okay, this blob here, that's aromatic. So that's all I care about. And in fact, with this formula, if we were given the formula for this thing, we would look and say, oh, that's an aromatic ring. No question, that takes care of C6 at least. I know I have another carbon, that must be over here. Let's look at this. Does that make sense? It kind of does. So we have the aromatic ring, we have one other signal. Our relative areas here, if we look at this, 1.5 and 1.5 is 3, and 1 more makes 4. I know from the formula that I have 8 total hydrogens, and so I have to multiply this by 2 to get up to my real number. So 3 and 3 and 2. And so we say then, well, what are these? What's causing these signals? And what the heck is going on with this splitting? Well, remember, if we were to go back and do our substitution test that I talked to you about in the beginning, we would know that the hydrogens sticking off of these positions are different to one another. We would guess that the hydrogens at the shoulder carbons next to the methyl group are the same. They're equivalent to each other, but they're just slightly different to the hydrogens at the second shoulders. And those are slightly different to the hydrogens, or one hydrogen straight across. So what are we seeing here? Well, okay, technically we have a group of hydrogens here. We have a different group of hydrogens here, and we have a third group of hydrogens there. So the hydrogens on the methyl adjacent carbons here, those make the most sense. We could say, okay, each one of these has one neighbor. It's going to be split into a doublet. No big deal. Likewise, the hydrogen at the far end of the molecule, we could say, okay, he's got one adjacent hydrogen in each direction. So one hydrogen here, that's going to be split into a doublet. No big deal. Or I guess a triplet here, two hydrogens that are equivalent being adjacent to it. So split into a triplet. So he's going to be split into a triplet. He's going to be split into a doublet. What about these guys in the middle? Well, they're split into a doublet by the left one and into a triplet by the right one. So a doublet of triplets. We would expect to see sort of 6 total peaks that are kind of messy. And the reality here is all of these are aromatic protons with nothing particularly strong separating them from one another. Our methyl group's not particularly electronically exciting. And so what we see is essentially these 2 doublet peaks and these 3 triplet peaks and all 6 of those peaks kind of overlapping in this mess. That's complex spin-spin splitting. They're overlapping, it's integrating kind of funny, it's a mess. Altogether, we do have 5 protons, but they're being lumped together in a strange way. So probably the 2 represent these bridgehead, these shoulder carbons, hydrogens first, and then the 3 integration is probably this other stuff that's just too close together to integrate properly. Another example of that comes in this sort of complicated molecule here. So we have several things going on, right? If we go through this molecule step by step, we've got the ones that make sense, I guess you could say. We have the aromatic protons that we'd expect to show up as kind of an aromatic blobby mess of nonsense up around 6.5 to 8.5. And in fact, that's all of this stuff and all of this stuff. Sort of a mess of things going on. In the middle of that, we do see the vinylic proton in green and in blue here. Those are really highly shifted, right? Normal vinylic protons wouldn't show up quite this high, but especially the green one is in between an alkene or participating in an alkene group and one step away from this aromatic ring. So it is shifted quite high. The blue one is shifted higher than we'd expect by virtue of being close to this aldehyde group. And so, we're shifted to the left here based on what even we would see in our table. And then we have our aldehyde proton. It's the first time we've seen one of those. That aldehyde proton, I told you, is one of the only things that's going to be shifted higher than an aromatic ring. And so we see it showing up over here around 9.5. I want to focus on the splitting for a minute. So our aldehyde proton in pink, if we look at its carbon, we go one step away, we see one hydrogen, the blue one. And so this is a doublet by virtue of having one neighbor. That blue one is being split in 2 different ways. It's being split by the pink one, and we would expect that to split into a doublet. It's also being split by the green one in this direction. We'd expect that to be split into a doublet. And so we get here what's called a doublet of doublets. How do I identify that? Well, look at the peak ratios here. This isn't a 1 to 3 to 3 to 1 kind of ratio that I would expect for a proper quartet. Instead, this is basically a 1 to 1 to 1 to 1 ratio. That's how I know it's been split twice and then each of those split twice again. That's a doublet of doublets. So this pattern, 4 peaks of equivalent height, that's going to tell us that whatever gave us this signal, this blue signal, has 2 separate non-equivalent hydrogen neighbors. So one to one side, in this case the green, and one to the other side, in this case the pink. If we go further and keep analyzing the green signal has only 1 hydrogen neighbor, and so it's split, as we might expect, into a doublet. And so we end up with a doublet for the pink, a doublet for the green, a doublet of doublets for the blue, and a mess of complex splitting for the aromatic ring. It's pretty typical. And so here's a picture of those 2 ideas. The quartet, remember, is based on statistics. So there's one way to get this arrangement, one way to get that arrangement, and 3 different ways, cut off here, but 3 different ways to get this arrangement. Whereas the doublet of doublets is essentially equal probability of going into one of 2 groups here, and then equal probability of splitting again. So pay attention to the ratios. Here's what that proton on C2 would have looked like. If its original signal based on its environment would have been at some delta value, so in this case about 6 3/4, we have one kind of splitting based on its interaction with the green proton. That has a coupling constant of 12 in this example, separates us here quite a bit. And then we have a different kind of splitting based on the pink proton, splitting each one of those peaks into 2. So we have a doublet and then more doublet. So we end up with 1 to 1 to 1 to 1 ratio of those 4 peaks. And so if we look at some more examples of complex splitting here, we're just going to show you a couple examples. Here's obviously a tough molecule. We have an ethyl group. We've seen what those look like. So here's our ethyl group. If we zoom in on that, we've got the D is a quartet and E is a triplet based on our splitting. So we know this is an ethyl group. Everything is shifted up based on the presence of that oxygen. So just as we'd expect. But now what's going on over here? These are the alkene protons. Technically, these are 3 different protons based on our testing. They're non-equivalent, but they're close. Proton, let's see, which one would be easiest to look at? Proton A and proton C, each of those have 1 hydrogen neighbor, so each of those is split into a doublet, like we'd expect. But proton B now has 2 different, non-equivalent, single neighbors. So B is a doublet of doublets. We can look at our splitting constants here if we wanted to pay attention to it. Ring structures also will sometimes show us complex splitting based on the rigidity of the ring. And so here's another example. These were taken from a little bit more advanced group, but I wanted to just show you sort of some examples of what this looks like. So again, everything is labeled out here. We've got, complex splitting happening on actually most of these positions. So you can take a look at this if you're really interested. If your brain's a little scrambly right now, fine, skip it. It's not a big deal. Most of our examples at this level are going to be fairly straightforward. So don't think about complex splitting first. Think about it last. All right, here we go. Another sort of simpler example, 1-chloro-3-iodo-propane. Well, what does this look like? Let's draw it out. I've got a carbon, carbon, carbon. There's propane. I've got a chlorine on one end. I've got an iodine on the other. And then, of course, I've got my hydrogens here. Okay, how many peaks do I expect? Well, hopefully by this point in the discussion, it makes sense that we've got 3 kinds of hydrogens here. I've got a 2 hydrogen peak here that's close to the chlorine. I've got a 2 hydrogen peak over here that's close to the iodine. And I have a 2 hydrogen peak in the middle that's kind of further from both. So I would expect 3 different signals. Now, how would they be split? This one on the left has 2 equivalent neighbors in that middle carbon. So 2 plus 1 is 3. I would expect a triplet. Likewise to the right, the iodine adjacent protons. I have 2 equivalent neighbors there in the middle. 2 plus 1 is 3. I would expect a triplet. So I'd be expecting 2 triplet protons there, or 2 triplet signals there. Then in the middle, I've got now splitting to the left pair of hydrogens should give me a triplet, but splitting to the 2 different hydrogens on the right should give me another triplet. So I should expect a triplet of triplets, or what would look like effectively 9 peaks. And so let's see what this looks like. Here is our actual spectrum. Let me clear my ink off of here. All right, so we've got our spectrum listed out like this. I do believe that this is labeled backwards. We would have A and C, it should be. I apologize for that. I lifted this picture. A and C would be our triplets for the left here. So this should be C. And then we have our mess of stuff over here. That's going to be our central ones. Now, you'll look at this and you'll say, well, that doesn't look like 9 peaks. True. It's going to be a mess of stuff. And so we've got some overlapping going on. The coupling constants between a chlorine and an iodine aren't going to be terribly different. And so we end up with a lot of overlap here. This is what I affectionately call a multiplet, rather than saying, you know, look, it should have exactly 7 or 9 or 12 peaks or whatever. I'll say, look, it's got a bunch of stuff going on that's complex. So with that little change here in our labeling, I didn't notice this before we started the video. There we go. We have our 2 halogen adjacent signals that are shifted quite a bit. We've got our central signal that's shifted less so. And the splitting makes sense. And so in terms of practical usage, we could think about things like this. You already hopefully know the answer to this question based on the alkenes chapter we studied in Organic 1, but does hydroboration oxidation yield primary or tertiary? So essentially, do we have the non-Markovnikov or the Markovnikov addition? Now, we know which one is correct, but we could analyze this by NMR to tell the difference, right? If we generated this product, we would expect a different NMR than if we generated the second product. And so here are the 2 spectra of those. The Markovnikov product would look like this. Essentially, we've got our methyl peak, we've got our alcohol peak, and we've got our cyclohexane stuff going on here. So what we're sort of seeing is the alcohol proton and all the other stuff sort of piled up. Now, if we generate this product on the top, the real product, what we'll see here is the presence of that hydrogen that's adjacent to the alcohol is much more pronounced. And then we get much more different stuff for our ring going on over here. So we see our alcohol proton, we see our alcohol adjacent proton, and we see the ring being separated out into much more distinct peaks. The point of a slide like this is just to say that there are practical applications to this. So what you'll see mostly in your problems is to look at sample problems, to look at things, you know, what do you expect for a certain molecule? How many signals do you expect? What does it look like? What would the splitting be? But in real practical terms, if a lab does NMR analysis quite a lot, they can use it to track reaction progress. Or if you're doing a new synthesis and you're not exactly sure what's going to happen, you can do the reaction, analyze the product, and come up with your hypothesis of what the mechanism was. So quickly here at the end, there's some sample problems. If we look at hexane, 6 carbons like this, symmetrical, so we only see 3 carbon NMR signals. We can see those all kind of showing up in the alkane range. This is also from SDBS, and it shows you which ones give which signals. So it's kind of a neat diagram. The highest ones here, in fact, are the middle two carbons, then the second set of carbons, and then the terminal carbons. What would we expect on a proton NMR for hexane? Well, again, because of the symmetry, 3 different types of signals. Here, those 2 internal CH2s would give us a signal. The carbon 2 and 5 protons would give us a signal that would be split into all kinds of crazy ways. And our terminal protons would give us a signal. And so we see, again, these are very closely linked to one another, so we see sort of a mess here. But in practice, we would expect to see 3 different signals and some splitting between them. How does it change if we throw in a heteroatom? Well, let's put a chlorine at the end. Now we lose our symmetry. And so now instead of having only 3 peaks on the carbon NMR because of symmetry, we now have 6. And just as we might expect, the carbon closest to the heteroatom is most deshielded. It's going to show up furthest to the left. So we've got carbon 1, 2, 3, 4, 5, 6. Likewise, the protons now are no longer symmetrical. And so we've got protons closest to the chlorine will be the most deshielded, and then B further on, C and D and E, and eventually F should all be different. What this is showing us is that as we get further and further away from that chlorine, it gets harder to resolve things. And so they're showing us what's going on here. So our closest hydrogens are there, our next group of hydrogens, complex splitting in there, and sort of all the rest are just sort of alkane hydrogens. If we now go ahead and put a chlorine on both ends, we get symmetry again. And so the exact positions of these peaks might be different, but we'll still see only 3 peaks on a carbon NMR and 3 signals on a hydrogen NMR, again with some splitting. And again, we see the hydrogens on carbons closest to the chlorine are most deshielded. Then the ones 1 step away are somewhat more shielded, and then further away, the internal hydrogens most shielded yet. So like all the other discussions we've had about spectroscopy and molecular analysis, this takes practice. So I encourage you to do the practice problems in your textbook, to go through and practice and look at the study guide and really look at all the examples available to you. If you'd like to look up real examples, you can go to the online database. Again, this is the SDBS, the spectral database I've referenced a few times and where a lot of the images in our PowerPoint have come from. So you can search for this, go in, punch in a molecular formula or a molecule name, and it'll come up with all the different kinds of spectra that are available from IR to NMR, mass spec, and then other things that we haven't talked about. So with that, I'll say keep up the good work, continue your practice, and reach out if you need anything. Have a great day.